Alright, in this video we're going to talk about the mole. The intention of this is to be a very quick kind of review. If you're new to it, you probably should check out other videos. I intend to make a more in-depth video on my channel, put it in the Chapter 3 playlist. But this is intended for people that just need a quick brush up that haven't seen this before. And of course you can skip around if you already know some of the gist of this. We'll end with the some sample calculations at the very end, but we're going to discuss what the mole is. A lot of people think of the mole and they think of the little animals that burrow underground, but that's not, of course, this particular type of mole. What we're talking about for the mole in chemistry is it's a number that's used to count with. And you're familiar with a lot of different types of these particular counting numbers. You know what a pair is. A pair is 2 items. And a quartet is 4, and a dozen is 12, and a score is 20, and a gross of things is a dozen, or 144 things. A mole is pretty much exactly the same thing as that, except when it deals with atoms and molecules, they're so small, even extremely small samples have tremendous numbers of them, trillions upon trillions, and so the number for the mole, the counting number, is very large. It is 6.02 times 10 to the 23rd countable things. Now, you can count anything with it. I mean, you could count cars with the mole if you wanted to, but if you had 1 mole of cars, that would probably have a mass of something like the Earth or something like that. That's a lot of material in there. This number is named after the scientist who developed the concept of it. They didn't know what the number was when he was working with it, but it's called Avogadro's number. It's extremely large, and if you take a look at maybe the longer video, or if you have me in class, we'll talk about the largeness of that number. But for right now, we will move along and continue talking about other topics. When you deal with the mole, a concept called molar mass comes up, and the molar mass is simply the mass of 1 mole of an element or a compound. Some people call that a formula mass, some people call that a formula weight, some people call it a molecular weight. Finding molar masses of elements is a piece of cake. It's just simply the atomic mass from the periodic table. We're going to round these off to 2 decimal places, but if you have me in class, the decimal places don't really matter. So if you want to know what the molar mass of carbon is, you go to the periodic table, you look up carbon, and it turns out it's 12.01. If you want palladium, you go to the periodic table, you look it up, it's 106.42. Units on this would be grams per mole, meaning that you would need 106 grams to have 1 mole, grams per 1 mole of a substance. So elements is a piece of cake. Compounds is a little bit more involved. So for compounds, what you're going to have to do is you're going to have to add up all the masses of the elements. So we start off with something simple, like sodium chloride. Look up the mass of sodium. There's 1 of them. Look up the mass of chlorine. There's 1 of those, and you simply add them together. 22.99 is sodium's mass, 35.45 is chlorine's mass. You add them up, 58.44 grams for every mole. Sucrose, common ordinary table sugar, C12H22O11. 12 carbons, 22 hydrogens, 11 oxygens. So you have 12 carbons times the mass of carbon, plus 22 hydrogens times the mass of hydrogen, plus 11 oxygens times the mass of oxygen. Again, all these numbers are from the periodic table, and the coefficients out in front of here are just simply the coefficients, or not the coefficients, but the subscripts on the formula. So the molar mass of sucrose, to have 1 mole of sucrose, you would have to have 342 grams. Sodium bicarbonate. You have 1 sodium, you have 1 hydrogen, 1 carbon, and 3 oxygens. So you take the mass of 1 sodium, you take the mass of 1 hydrogen, you take the mass of 1 carbon, and 3 times the mass of oxygen. That gives you a mass of 84 grams to have 1 mole of your substance. Finally, you have ammonium sulfite. And if you're unfamiliar with the parentheses act just like a multiplier. So this 2 out here in front of the NH4 means that there are 2 NH4s. So you have an NH4 and another NH4. So this 2 can be thought of as a multiplier. You can distribute it throughout here. There's an invisible 1 behind this N, because you don't have to write 1s when you write chemical formulas. And so 2 times the invisible 1 is 2 nitrogens, and 2 times 4 is 8 hydrogens overall. So 2 times the mass of nitrogen, plus 8 times the mass of hydrogen, plus 1 mass of sulfur, plus 3 masses of oxygen. You can also just find out what the mass of NH4 is by taking a nitrogen and 4 hydrogens, adding those up, and then multiplying it by 2. And that would be the formula here, where you take sodium plus 4 hydrogens, find out what the mass of one NH4 unit is, and then multiply that whole thing by 2, because there's 2 NH4s. Either way, you're going to get 116 grams. All right, so how are we going to use this? The purpose of this is to focus on this first equality here. We need to know how to convert back and forth between moles and mass. In chemistry, when you're doing chemistry experiments, you need, well, let's backtrack here a little bit. When it comes to like chemical reactions are happening on a molecular basis, molecule to molecule, or 2 molecules to 3 molecules, or something like that. So, like I said, it's a counting number, the mole is. So if you're talking about molecules, you can talk about moles. We don't have a way to measure moles in the lab. There's no device to do that. But there's a relationship between mass and moles that we've just been talking about. There's a relationship there. So we have scales to measure mass. So we're going to use scales to measure mass, and then we can convert to moles. The more complicated or the longer video, we'll talk about how to convert using particles. But particles aren't as useful to us as moles and mass are. So we're going to be talking about this first equality right here. And here is our first sample problem where you have 26.36 grams of carbon, and I wonder how many moles that is. This goes back now to conversion units, and if you haven't had those, you can invite yourself into the playlist for Chapter 2 when I talk about how to make unit conversions. The way I teach unit conversions is you always start with what you're given, which is 26.36 grams. Set up your conversion factor, which I use sets of parentheses. Some people use T-charts. I'm not a fan of T-charts. Inside the parentheses, you always let your units do the rest of the work. So the question is, what unit goes where? Well, what unit do you want to put on the bottom is the unit that you want to cancel from outside. So the grams are on outside. I need to put it on the bottom of the conversion factor because this is like grams over 1. I want to cancel grams out, so grams goes to the bottom. That means moles are going to go on top. Once the units are in, now you can bring the numbers over. And if I'm going to backtrack here just a little bit, I'm going to go back to this equality. The numbers in front of here on the equality go with whatever unit they're with. And so I'm going to pull the 1 for moles, and you see where it says a molar mass. Well, a molar mass, there isn't a number there. You can't just pull off any number. Every substance is unique in its molar mass, as we just saw in the previous slide, where we calculated all of this stuff. So every substance has its own molar mass, so you can't just simply plug in any number. So this means a molar mass, you need to figure out what the molar mass of your substance is. So now going back to here, we've set up our grams to the bottom, moles on top. 1 always goes with moles, as we just said just a little bit ago. And since this is carbon, we're going to go to the periodic table and we're going to look up the mass of carbon, 12.01, and that's what we're going to put on the bottom here. And now we can make our calculations here. So if I put in, and let's get the whole calculator on here as much as I can, 26.36, and I'm dividing by 12.01. And again, the decimals don't really matter until you're actually doing real lab work with real scales. Oops. And I want to hit the enter key on that, and you get 2.19 moles. And so our answer to this problem, grams cancel out, and you get 2.19 moles of carbon. Which makes sense, because if I had 2 moles of carbon, I would have about 24 grams. And I have a little bit over 2 moles, because I have a little bit over 24 grams of that. So it makes sense that I'd have over 2 moles of carbon. Let's take a look at sample problem 2 here, and this will be the end of this video. What's the mass of 0.7 moles of NH4,2SO4? This is called ammonium sulfate. We're going to go moles to grams. So I first write down what I've been given, which is 0.75 moles. Set up my conversion factor. What unit goes to the bottom? Well, it's what I want to cancel out. So moles goes to the bottom, grams is on top. 1 always goes with moles. Grams is relative to every substance, so I need to figure out the molar mass of NH4,2SO4. So I have 2 nitrogens times the mass of nitrogen, 8 hydrogens times the mass of hydrogen, 1 mass of sulfur, 4 masses of oxygen, 132.16, that goes up there. And now I can calculate the final mass here, and I'm going to go ahead and cancel out moles. Moles are going to cancel out, and when you calculate it, you should get 99.12. And I'll show you that here real quick. 0.75 multiply by 132.16. 99.12 grams. All right, I hope this helps. And if you have any questions, you can ask in class. And again, this is meant as just a general, real quick refresher on how to do mole conversions. Thank you.